Hello everyone and welcome back to Networks class. Last time in class we just finished up discussing the Ford-Fulkerson algorithm. In particular, we talked about its runtime a little bit. And then for most of class we discussed some applications of max flow. So the two applications that we looked at were the producer-consumer application and how to find a feasible flow when we have some lower bounds on the arcs. And the plan for today is to first go over the homework assignment 3.2. So that was the second homework assignment for the drug lord problem. And then we'll discuss the projects, which is basically going to be your main homework assignment for the remainder of the quarter. And to facilitate your projects, instead of continuing with some max flow applications, what we're going to do is discuss interdicting max flow, and we're just going to get to start this at the end of lecture today. We won't get all the way through it. And then kind of the long-term plan is after we talk about interdicting max flow to go on to discuss min-cost flow for a little bit. And when we're done with that, we'll go back to looking at some applications of max flow, etc. So that's the plan for a lecture for today. So let's just get started by going over this homework assignment 3.2. So in this homework assignment, we took our basic drug lord and we added some evasion probabilities to make him a little bit more realistic. So in problem 1, we had to turn the distances that he travels into evasion probabilities. So the key to this problem is really this assumption here that says that for every hour on the road, there's a 1% chance of being pulled over randomly. So we have to use that assumption to figure out the transformation from hours into probability of evasion. So to do this, you can do something like this. So the assumption is that e to the minus r times hours is equal to the evasion probability. And we want that 1 hour gets turned into a 99% probability of evasion. So using this equation, you can go and solve for what the constant r should be for that problem. So that's basically problem number 1. And you can see the kinds of numbers that came out of my transformation. In problem number 2, we're just applying the minus log transformation to turn these probabilities of evasion into something we can solve with the shortest path. In problem number 3, we're just computing some kind of escape routes. So here's a basic escape route that the drug lord could take out of the state. And the key to number 3 was taking the objective function of the shortest path, which is this z, and turning it back into an evasion probability. So when you get this z out, it's going to be some kind of minimum log kind of thing, minus log kind of thing. And to turn it back into an evasion probability, we have to take the negative of it and take the exponent to do that. So just to show you what this means, basically what's going on is that z is equal to the sum of minus log of these evasion probabilities. And what we want to do is find the evasion probability over the whole path. So z is just the sum over all edges of the evasion probability on this edge e. And so if we do e to the minus z, what we're going to be getting is e to the minus sum over all edges in the path of this minus log of the evasion probability. And then these negatives cancel. We can use the log product rule, so that's equal to just e to the log of the product over all edges in the path of the evasion probability of that edge. And then e and log are inverse functions of each other, so that's just equal to the product over all edges in the path of the evasion probability for that edge. And this product is exactly the evasion probability over the whole path. So that's what was going on in that problem. So that was number 3. In number 4, we're going to place some roadblocks, assuming that Tihomir has a 100% chance of getting caught if he gets run through a roadblock. And the question was to plot an operator resilience curve, so that's what the operator resilience curve that I got looks like. In question number 5, I ask you, is anything different about the escape routes and the roadblock locations that we're computing now versus the ones in the previous homework assignment where we were just looking at distances? And it turns out that no, there isn't any difference between these roadblock locations and the ones we computed before. So let's see why that is. So what basically happened was the following. That we started out with distance, and the way that we turned distance into evasion probability was with our formula here. So we had some constant that we're multiplying distance by, and this was evasion probability. But then the next thing that we did was we took the minus log of the evasion probability to be able to stick that into the shortest path. But if we combine these two, what we end up taking is minus log of e to the minus r times the distance. And you can see what's going to happen here. So exponent and log are inverses of each other. The minuses cancel. And so what we get is just r times the distance. So all we did with these two transformations was we took the original distance and we multiplied it by some constant. And that's why we're getting the exact same answers. Essentially, we're solving the same shortest paths. We just changed the units of everything by multiplying everything by this constant. And that's why all the shortest paths are looking exactly the same. All of the computed roadblock locations are looking exactly the same. So in the next question, I ask, what if we were to change the assumption that for every hour on the road, there's a 1% chance of being pulled over randomly? Well, the only thing that changing this assumption does is it changes this constant r. And so it doesn't matter what that constant is. It could be 0.5, it could be 500,000. We're still going to get the exact same paths and the exact same roadblock locations. So changing that assumption is going to change absolutely nothing about the answers that we get out of this problem. So number 7, we're changing the realism, or we're increasing the realism of our model slightly by modeling the fact that if he runs away to another US state, there's going to be a 75% chance of getting caught. And you can do this just by adding 25% evasion probability from the arc from other US state to escape, for example. And so what happens when you do this is that he immediately starts running away to Mexico. And he runs away, or the push for him to run away to Mexico is very strong. So when we have 5 roadblocks in place, he can only run away out of Flagstaff in the north direction. But what he ends up doing is he runs away north, but then he swings back around so that he can come back down to Mexico. So in number 9, I ask you how many roadblocks, or what happens at 6 roadblocks. Well, at 6 roadblocks, we can cut off Flagstaff, and that may not be too realistic. So here we're saying that he has some lead time on us, and so we might not be able to put roadblocks just outside of Flagstaff. So to do this, we can just introduce a constraint like this that basically says all of the arcs going out of Flagstaff have to have no roadblocks on them. So once we add this constraint, the mixed integer program is no longer going to put roadblocks on those arcs coming out of Flagstaff. So in number 10, I ask you to solve this for a range of roadblocks between 0 and 20. And how many roadblocks do we need to cut off Tihomir's escape completely? Well, it turns out that we need about 13. And what interesting thing happens when we move from 5 to 6 roadblocks is that from 5 to 6 roadblocks, we can cut off his escape to Mexico. And so at 6 roadblocks, he ends up having to escape to another US state. So in number 11, I ask you to do some plotting to see what the results would look like. So here are some of the results of my plots. So here you can see with one roadblock location, we just place the roadblock here. With two roadblock locations, we place it there. This is what happens with 5 and 6. So with 5, we can't cut off all of his escape to Mexico, but with 6 roadblocks, we do. And the interesting thing to see here is the fact that down on the bottom right-hand side of this map right here, there's a big mess of nodes and edges. And so if he gets to this location, he's basically going to run away and we won't be able to stop him. But what happens is we actually cut him off before that. So we place the roadblocks up here, which stops him from getting down to this part of the graph. And so essentially, regardless of what's going on down here, like we could have been much more careful here in terms of nodes and edges, and it wouldn't have mattered. We would have gotten the exact same solution. And these bottom two solutions are what happens when we have 12 and 13 roadblocks. So with 12 roadblocks, we see a roadblock plan like this, which still leaves him an escape route through here. But with 13 roadblocks, we kind of close in on Flagstaff, and we're able to capture all of his escape routes. So in number 12, I ask to add a little bit more complication to the kinds of roadblocks that we can do. So let's say that each city can only place one roadblock on an arc going outside of it. So the way that you can model that is with constraint like this. So the key point here is to get you to introduce into GAMS a constraint that depends on the nodes. So here's kind of a set of constraints that we're introducing, one for each city, that says that the sum of all the roadblocks arcs going out of the city has to be less than or equal to 1, meaning that that city can only block one arc. And you can see that this does indeed have a change on the answer. So with 6 roadblocks, we can still block his escape to Mexico, but we can't ever block his escape from the state entirely. So there's always a way for him to figure out an escape path out of the state. So number 14 is perhaps the most interesting question on this homework assignment, which are what are some of the things that you could do to kind of make this model be better? So there's lots of things you could do. Simple things are we could add more nodes and arcs, but this may not change the answer. We could be more careful about the input data distances because right now all of the distances in the model are just computed from these abstract map units. So we could go and use Google Maps, but likely that won't change the answer very much. One important difference is we could change the rate of detection on some roads versus others. So maybe there's a higher rate of detection on the highways and a lower rate of detection on some kind of side roads. And that's definitely going to make the drug smuggler take different routes as he runs out of the state. We could reduce the likelihood that Tihumir is discovered at a roadblock. So we did this in the previous homework assignment with kind of having weaker roadblocks. We could be more realistic about our roadblock constraints and the fact that blocking some roads is more expensive than blocking others. So what I mean by that is suppose that we have 30 policemen and blocking one road takes 5 policemen because it's kind of a big road, but blocking a different road takes only 2 policemen because it's a small road. So the way that you could do something like this is by introducing a constraint like this. So Qij is going to be the number of policemen required to block arcij. So we have the sum of Qij, Xij has to be less than or equal to 30. So by introducing a constraint like this, we're saying we have 30 policemen total, and if you want to block this arc, you have to use up Qij of them. And so this is kind of a very useful modeling tool because often it is in fact more difficult to attack some things than it is to attack others. So you can do that by introducing these kinds of budget constraints. But let's talk about another interesting twist on this problem on how we could have made it more realistic. So one thing we could do is kind of introduce time into the problem. So, and And we could give the drug smuggler the option of not necessarily running away out of each town, but maybe staying in the town for some amount of time. So the way to picture this is imagine placing the Arizona map on its side. So each of these circles represents Arizona. So this is Arizona in time 1, Arizona in time 2, and time 3, and time 4, and so forth. And now out of Flagstaff, he has the option of going to various other locations, or he has an option of staying in Flagstaff for this time unit. And then in the next time unit, he similarly has options of moving or staying in that particular node, in that particular city for a time unit if he chooses. So if we take a graph like this and stick it into GAMs and do interdictions on the edges, we would have different meanings on the interdictions. So if we choose to interdict this arc right here, what it would mean is to interdict this highway at a particular time. So it means put up a roadblock on this highway at this particular time. And if we placed an interdiction right here on this vertical arc from Flagstaff to Flagstaff, what that would mean is send a team to search for the drug smuggler in Flagstaff at this particular time. So this would be kind of a significant increase in realism and complication in our model that we could do as a next step in terms of making this more complicated. So that's the basic idea of this homework assignment. So now let's discuss our second thing for today, which is the plan for the next few weeks in terms of your projects. So in terms of your projects, the final deliverables will look something like this. First, your team will have to do a 21-minute in-class presentation, followed by 4 minutes of questions and discussions with the audience. And so the key thing to notice here is that 21 minutes is a significant amount of time. So the key here is to produce good and interesting content that can fill up that amount of time, and you can really tell something interesting to the class. So as part of the deliverables, you'll hand in the PowerPoint slides for your presentation. And we'll post these online so that people in general can see the kinds of analysis that you've done. And we'll also have a 3-page executive summary where essentially you just describe the problem, you describe the analysis that you did, and the general results that you got to. And we'll post those executive summaries online as well. And the final part of the deliverables is to just turn in all the GAMS file and the data and CSV files that are required to essentially repeat all the analysis in your project. And the reason for this is because sometimes these projects end up getting turned into theses in later quarters, and so your GAMS file might be useful to another student in terms of a starting point for doing a similar kind of analysis. And of course, I'll hand out more instructions on submitting these as the presentations get closer. But let's discuss kind of the general steps that you'll have to go through to complete your project. So some of these you've seen because they were part of the short due dates that we've had thus far. So the number one step is to create an interesting backstory. And this is really important because all of your analysis questions are really going to be derived from this backstory. So it's this backstory that's going to make you ask realistic questions that then you'll have to turn into mathematical models. So the second part is to mathematically model your network operation. And so you should have already begun thinking about this. So in particular, you're going to write a linear program for the network's operation. And the key here is to have a meaningful measure of effectiveness on what it means for the network to be functional. So for example, if you're doing some kind of big airline, a typical thing that an airline wants to do is move customers from the various demand points that they have customers coming into their network to where those customers want to go. So, for example, they want to move customers from Chicago to LA and Chicago to Seattle, but at the same time, they want to move customers from Seattle to LA and from Seattle to Chicago. So, they have traffic in all kinds of directions on their network. So, a max flow model for an airline for Chicago to LA wouldn't necessarily be appropriate because that's not what the airline is trying to do. And so, definitely thinking carefully about exactly what the measure of effectiveness is and the right way to mathematically model your network is an important part of the project. So, the second or the third step is to create some data for your network. And so, you should have already had a start on this in terms of creating some CSV files. Step 4 is to create a GAMS model for your network. So this is just to run the LP that you figured out in step 2. Step 5 is a new step that you may not have seen before. So in this step, you're going to model either attacks on your network or some kind of a design on your network. In terms of attacks on your network, what you're going to have to do is create some kind of min-max problem or max-min problem where the outside problem is the attacking variables. And then you're going to have to do the dual trick to be able to turn this problem into something you can stick inside of a solver. In terms of designs, you don't have to do the dual trick because this outer design part is going to have actually the same objective as the inner problem. Because, the operator is both the person placing the warehouses and doing the routing afterwards. If the design of your network is, for example, where to place a warehouse or something like that. So design isn't easier or harder than attacks, it's just different. But also, some of you may have the idea of doing first a design, and then an attack, and then an operation of the network. And that 3-stage kind of problem is much more difficult than these other two. So if you want to do this kind of 3-stage problem, come and talk to me, and we can come up with some ideas on how to do that. The next step would be to take these design ideas that you have and to stick them into GAMS so that you can actually compute attacks on your network and compute designs on the network. And step 7 is the most important step, which is to do some meaningful analysis, meaningful and interesting analysis on your projects that you can take tell the class about. So here you're really totally open to do anything that you think is interesting, that you think would be a good learning experience to tell everybody else about. So some other guidance about the projects is that besides myself, the department has a number of other optimization faculty. And so these are great people to talk to about your projects. So you can go and ask them for some help or some guidance on how exactly to model these things, how to do the things that you want in GAMS. They'll be very happy to help you with that. And the final piece of guidance about your projects is the following. When you graduate from MPS, you'll be in a unique position because you'll both have to produce analysis and you'll have to evaluate other people's analysis. And that's why as part of this project, we'll do a little bit of peer evaluation. So what we'll do is, in about the middle of next week, we'll have you create kind of a preprint of your executive summary. And we'll take that preprint and I'll give it to some other students in the class. And those students will write an evaluation of your preprint. So they'll say what they like about your project, what they don't like, what they don't understand. They'll give some ideas on how to make it better. And then you'll get those evaluations back and you'll have about a week to incorporate that into your projects and to extend your models. And partly the reason that we're doing this is because when we talk to the people that you'll be working for when you graduate from the program, the number one thing that they told us they want out of graduates is good communication skills. And partly we're doing this because it's much easier to evaluate communication when it's somebody else's communication. It's much harder to evaluate your own communication. And so hopefully this peer evaluation will give you some feedback on your communication in your executive summaries and feedback that you can actually take to improve your projects. So in terms of the timeline of what you should be doing in the next few weeks, in general, I'd like to not have many due dates because I want to let you manage your own time. On the other hand, I found that if I don't have some due dates, then work just doesn't get done. So these are the kinds of ideas you should be thinking about in your mind and the kinds of dates you should have in mind. So in about next Monday, you should have a working GAMS code for meaningful attacks or design analysis. At about next Wednesday, you'll have to write this preliminary 3-page executive summary that I'll hand out to your classmates for evaluation. On Friday, you'll get the feedback from your classmates. And then you'll have about a week after that to expand your model and feature new aspects of reality, to edit your analysis and create a presentation. And we'll do presentation in the final week of class. And of course, I'll pass out more guidance on all of these steps as they come up. So that's basically the plan for the next few weeks of class. So let's go on to the last part of lecture for today, which is just beginning to discuss max flow interdiction. So in discussing this, we'll be able to pull out some general rules for how to do interdiction problems, but we won't get all the way there today. So let's just discuss some ideas on how to do max flow interdiction and what works and what doesn't. So here's our typical max flow problem. So we have to maximize over the variables v and y. We want to maximize v, and we have some kind of network flow constraints that act on these variables y and v. And you're very familiar with what these look like. That's why I'm not writing them out. It's all this stuff that says the sum of the trucks going into a node has to equal the sum of the trucks going out. And then we have some capacity constraints that look like this, yij less than uij. And we have some non-negativity constraints on the y's. So this is our general max flow problem. And what we want to do is figure out a way to attack a network that's doing max flow. So to do this, we're going to introduce binary variables exactly like before that are going to mean do we attack arc ij. And these variables are going to have the opposite objective of the inner problem. So the network's trying to maximize flow. So the x variables are going to try to minimize flow. And of course, the x variables might have some kind of constraints on them. So something like I can only attack 5 arcs, so the sum of the xij's is less than 5. But of course, these constraints here that just involve the x variables, you already saw in the homework assignment, these could be arbitrarily complex. So in the assignment, we had things like you could only attack 1 arc out of every city, and you can have all kinds of very complicated constraints on what you're allowed to attack and what you're not allowed to attack right here. But probably more importantly, the question is how do the x variables interact with the y variables? And one very natural idea to have is to write something like this. So to just multiply these capacities by 1 minus xij. So if we do this, what happens is that if the xij is 1, this capacity becomes 0. And if the xij is 0, this capacity is just the original capacity uij. So conceptually, exactly like we wanted, if we attack an arc, the flow can't use that arc. And if we don't attack the arc, it can use the arc the same as it originally did. So conceptually, this is a great idea, but it doesn't quite work. And the reason that it doesn't work is the following. So imagine trying to solve this. So to try to solve this, we'll have to take the dual of this inner problem, because that's the only way we could get the objective function for all of these variables to align. And so when we take the dual, what's going to happen is we're going to be multiplying this right-hand side by this dual variable. So the dual is going to look something like this. minimize over x, rho, and pi. And then we're going to have as an objective something like sum over uij, or sum over arcsij, uij 1 minus xij, pi ij. And we're going to have some constraints here that come out of the dual. I won't write them out because they're not important. The important part here is, and the reason that this idea doesn't work, is because the objective here is nonlinear. And the reason it's nonlinear is because we're multiplying x variables times pi variables. And so we can't use our nice linear programming branch and bound ideas to go to try to solve a good attack plan. So even though intuitively and conceptually this is a really nice idea to write this down, computationally it doesn't work at all. So let's see a different idea that does work. So let's begin again with our max flow equation. So maximize over V and Y. We have our network flow here again. We have capacity constraints and non-negativity constraints. Outside, we're going to have the x variables that are trying to minimize, and the x variables have some kind of constraints on them. But now, when we attack an arc, instead of dictatorially saying that the flow cannot use that arc through a constraint, we're going to do that through an incentive in the objective function. So what we're going to add here is sum over arcsij, some kind of penalty times xij, yij. So these d's right here, you can think of them as a penalty for putting flow on the arc. So let's just, with a picture, imagine what this penalty terms here is actually saying. So we have a graph here and the node S and the node T. And imagine some arc in the middle here going from node I to node J. So the operator of the max flow problem, they could potentially put some flow on this arc from I to J. And if they put some flow on this arc, they could potentially increase their total flow from S to T by 1. So if this penalty right here, if this penalty is 1.1, what we're saying is that if I attack the arc, for every unit of flow you put on it, I'm going to subtract 1.1 units from your total flow. So basically this incentive is, or this penalty is so big to give a disincentive for putting any flow on that arc. So just by making this penalty 1.1, we can ensure that any arc that we've attacked is not going to get any flow. On the other hand, if this penalty were something like just 1, then what's going to happen here is that the operator is going to be indifferent for putting flow on the arc versus not putting flow on the arc. And so you might get some solutions that put flow on the arc but have the right objective function value as though no flow was going in the arc, because we're subtracting out any flow that's going on an arc that's attacked. So that's the basic idea. We're going to use these incentives instead of the dictatorial way of doing this. And the reason for this is because now when we do the dual trick on this inner problem, this right here is just going to come down on the right-hand side of the dual. And since it's on the right-hand side, everything's going to be nice and linear, and we'll be able to use linear programming to actually compute attack locations for max flow. So that's as far as we're going to get today. Next time we'll discuss this a little bit more, and we'll pull out some general rules of thumb about how to do interdictions for essentially any network problem, not just shortest paths and max flows, but anything in general. So thanks a lot for listening, and I'll see you all next time.